Hi everyone, this is Mr. Youngren, and this is lesson 6 in our third unit. In this unit, we're going to be writing equations from tables of quadratic functions. So the standards that we're working on are writing the equation of a quadratic function from a table of values, and then also writing the equation of quadratic functions given information from various contexts. So before we get into that, I'm going to have you work through this opener. For the opener, you're going to work with tables just like we always do, finding changes in y's and changes in x's. Look for the patterns to identify whether it is a linear or absolute value. It'll only be one of those two. And then after you've identified what function, go ahead and write the equation. So go ahead and hit pause and work through the opener, and then we'll talk through it here in just a moment. All right, so here's all the work that just even I had to do to figure out what type of function and then also the equation for each. So let's talk about them. Here in this first table, I'm looking mostly with the changes in y's and changes in x's. And I noticed that they're going up by different amounts. So I'm like, you know what? I can't assume that this is non-constant because I know for something to be constant, I need to check what is each change in y divided by each change in x. So that's what I've done in these three changes in y's divided by changes in x's around the table. I've checked what is change in y divided by change in x, and each time I'm finding that I'm getting -3, telling me that this is actually constant, right? So even though it appears that they're going up by different amounts, it actually is constant once we check all the change in y's divided by change in x's. So since it's constant and we do not see us ever switching from subtracting to adding, that there's nothing to suggest that there's a turning point. So this function is linear because it's constant with no turning point. So the linear function, we need the slope and then just any point from the line. So I went ahead and circled 2, 8, just to say I'm going to use that point and that there's no particular reason. So our equation is y equals, I put -3 divided by 1. That way, if we were to graph it, I have a rise over run. And then our point, x minus 2, the sign of the x-coordinate always switching, and then plus 8. Over for b, again, same idea. I noticed change in y's and changes in x's are going up by different amounts. So I went ahead and checked what are all those changes in y's divided by their changes in x's. Each time I found that it was either 2 or -2. So in this case, it is showing that it's constant, but since we're switching from adding to subtracting at some point, that tells us there's a turning point. Now I found that turning point by going directly in the middle from where we switched from adding to subtracting, which is when x is 5 and y is 14. I also used the symmetry and saw that there was a 10 above and below that turning point. Now, one of the things we've got to work on here, after we've identified that its absolute value from it being constant with the turning point, is the sign in our equation, right? And since we do both, we've got to really check what is the graph showing us. So I just made a quick sketch. The vertex or turning point would be right 5 and up 14. I'm like, okay, to go to the next points, I'd have to go left 2 and down 4, or right 2 and down 4. So in both cases, I'm having to go down from that vertex. So that tells us the graph opens down, and thus our slope or a value needs to be negative. So the full equation is y equals -2, absolute value of x minus 5 plus 4. If we wanted to, we could put this over 1, just so again we have a rise and a run. All right, so now that we have reviewed our other two tables, let's go ahead and jump into our third set, which is quadratics. So quadratics, we need to kind of review a couple of the properties that we had learned prior. So let's look at remember the relationship between the a value and the rate of change of a quadratic function. So the rate of change of a quadratic function can be found by finding the second difference. From a table. Now, if we remember what that is, we have all of our y values, and then all of those arrows that we draw initially are changes in y's. That second difference is what we see after the change in y, so the pattern that we see of what we have to add or subtract to get the next change in y. So because of this, we actually have to do a little work to find the a value, right? So the a value is going to be the second difference divided by 2. Or, since this second difference helps us describe the rate of change, and it's how we find it in the table, we can just say the rate of change divided by 2. And now it'll give us this A value, right? There's also another way that we'll be able to find it, and I'll talk about that once we get into our first example. So again, whatever we find as a second difference is not what we're going to put in the equation. Rather, that value of the second difference divided by 2 is what will go in our equation. So let's go and try this out. So first thing, we'll always find our changes in y's, changes in x's. And as we go through these, let's pretend as if we have no idea what type of function. That way we're getting the habit of checking for that. So 10 to the 4 minus 6, 4 to 2 minus 2. Then I'm adding 2, then I'm adding 6. So since I went from subtract and adding, I know for sure that there's a turning point. I also can use the symmetry, seeing 4 above and below, and 10, 2 above and 2 below. The x's, I notice I'm adding 1. So I know for sure all the change in y's divided by change in x's are at least getting me different amounts. We're not getting the same amount. We can say that for 100% positivity. So now what we need to do, this over here, what we just found, are our change in y's. To find the second difference, we've got to look for a pattern as to how do we go from one change in y to the next. If this is constant, if we can find a value that we need to add or subtract, then this tells us that it is quadratic. So this is what we're looking for in the second difference. So from negative 6 to negative 2, I'm adding 4. Negative 2 to positive 2, I'm also adding 4. And 2 to 6, once again, we are adding 4. So this second difference is our rate of change. Okay, that's the same thing, right? That's how we would describe the rate of change, is that is increasing by 4. The A value is 4 divided by 2. So it's 2. And that's what we need to use in the equation. Okay, so that's the biggest difference, or at least the one additional thing we're going to have to do with quadratic tables. All right, so our vertex or our turning point we already identified as 3, 2. And so our equation is y equals 2, not the rate of change, but the A value, dividing the rate of change by 2, x minus 3. We have to square it. That's what makes this quadratic. We don't have the exponent of 2 outside our parentheses. This is not quadratic. And plus 2. All right, so just like all of our other lessons, we're going to go ahead and plug in an x value and see what we get for y. So 9 minus 3 squared plus 6. So thinking about order of operations, doing 9 minus 3 first. I think it's 6. Next, PEMDAS. The E is for exponents, so 6 squared is 36. We have PEM for multiplication, so 2 times 36, 72. And then plus 2 is 74. All right, you have a table below. I'm going to ask that you hit pause and try this one on your own. Even if you're not following exactly, at least work with your change in y's and changes in x's. Do some of the work. And then once you've tried your best, go ahead and come back and we'll work through the next problem together. All right. So again, as we go through these tables, act like you're not sure what type of function. So things we should have noticed initially is that all of the change in y's divided by change in x's are different amounts. We are also switching from subtract or adding to subtracting. So this is non-constant with a turning point, telling us that this is quadratic. Or at least, right, we know it's not linear absolute value. We're going to prove that it's quadratic by seeing if the second difference is constant. So I went ahead and when I noticed, I went from adding to subtracting, circled when x is negative 2 and y is negative 5 as our vertex or turning point. And then I checked my change in y's, do I see a pattern for the second difference? So what I'm noticing is that from 9 to 3, I'm subtracting 6. From 3 to negative 3, also subtracting 6. And same from negative 3 to negative 9. So our second difference is constant. Now confirming that this is in fact a quadratic table. So the rate of change is that second difference, so negative 6. The A value is that rate of change divided by 2. So negative 6 divided by 2 gives us negative 3. We've already identified the vertex as negative 2, negative 5. So just placing everything in our equation. -3 is the a value. It's x plus 2, switching the sign on the x coordinate, making sure we square the parentheses. That's what makes this whole equation quadratic. Then -5. Now, when we plug in -10, I went ahead and dealt with the parentheses, the first part of PEMDAS, and now we need to do the exponent. And just one thing to remind ourselves of is when we square a number, the result always needs to be positive, right? A number times itself is always going to be positive. Negative times a negative, always positive. A positive times a positive, always positive. So if I plug this into my calculator and I forget that fact, the calculator, it really just tricks us. So what the calculator is doing is it's saying, I know what 8 squared is, it's 64. And the way that you've typed it in, exponents comes first in order of operation. So I'm going to square 8 to get 64 and then multiply it by the -1 in front. So that's how the calculator is getting -64. So that's just something we need to remember. If we want to avoid that, we can put -8 in parentheses and then square it to always get the outcome that we want. That is +64. And now, when we take 64 and multiply it by -3, we're going to get a -192 to subtract, or then subtract 5 away from that to get -197. Right, so something we got to be careful about and think about the work that we're doing. All right, let's go ahead and grab the next page. We're going to go ahead and just do this top portion. Very similar to what we did with absolute values. If I give you a description, can you go ahead and write the equation? So there are going to be some things that give us these things away to describe a quadratic. Other times we might just assume that it is quadratic. So everything a little bit different. So it opens up, has a rate of change of 6. Remember, that's not what goes in our equation. We need to take 6 divided by 2 to get 3, and that's our a value that we want to use in the equation. And then we have our turning point. So it's y equals x. Oops, let's try that again. Y equals 3 x minus 5, switching the sign, always squared, and then -6. Right, next one opens down, telling us that a is negative. Shifted to the left 2, it's talking about our turning point there, so that means x equals -2. And down 3, so that's our turning point or vertex. Y is -3. And the rate of change is -4, but we need to divide -4 by 2. So we get a -2, which aligns with what the a value is describing us. So y equals -2, x plus 2 squared minus 3. Right, parent function, again, that is the most basic quadratic there is, which is x squared, where the vertex is at 0, 0. And if it is reflected over the x-axis, that means we are making it negative. So the equation would just be -x squared. Right, and then the last one opens down, telling us that a is negative. Shifted to the right 21, that means x is +21. Up 33, x is +33. And an a value of -1/2. Now what's nice about this is the a value is what we use in the equation. So I don't need to go ahead and divide this by 2. This is exactly what we're going to use. So y equals -1/2 x minus 21 squared, switching the sign, and then plus 33. All right, that is it for lesson 6. Make sure that you do the video check-in. Have a great rest of your day.